Hello again. We started this discussion on is my structure safe, and then discussed many things about performance-based design. And one of the questions that came up during the discussion was that often people, the public or the client, would like to know what level of earthquake or what magnitude of earthquake is their structure designed for. And this is a really, really simple question from their point of view. It's a valid question, but unfortunately, we structural engineers may not have a very direct or simple answer to that. First of all, why do they want to know? Because whenever there's an earthquake anywhere in the world, a strong earthquake, they see pictures like this in which the buildings have fallen, people have been injured or they've lost their life, and the whole communities are destroyed, so they get worried. What will happen to my structure if an earthquake of that kind happens? So obviously the question comes up, what level of earthquake or what magnitude of earthquake my structure can resist? So this question is what we are going to try and address. Before we go to earthquake, let me talk to you about another very simple question. Let's say you are interested to read a book in a dark room, in a room, and you want to buy the right light bulb with the right wattage. So you go to an illumination engineer or electrical engineer, and then you say, I would like to buy a bulb to read the book. Can you tell me what should be the wattage of that bulb? This is a simple question, and there should be a simple answer. But the illumination engineer might ask you, how far will you be sitting from the light? Will you be facing the light, or will the book be facing the light? How good is your eyesight? What will be the color of the page that you will be reading? Will it be white or black? What will be the font size? How many other lights are there in the room? Because this all will impact the light actually coming to your book that you're going to read. So earthquake design is very similar to the same problem, and we will come back to this analogy one more time. Once again, a simple question, very difficult to answer unless we know a lot more about the problem. First of all, let's go back to the basic. Why earthquakes happen? What causes earthquake? I think all of you who are listening to this one, I'm sure you're already aware about the reason the earthquake happened is because of the movement of the tectonic plates, because of the faults that are generated, and they move and they accumulate energy when they cannot move, and then suddenly move, then you get earthquakes. So that we know, and there's so many plates and some movements around the world. So once an earthquake happens, then there are four things that can be related to that earthquake event. Number one, how is it measured? What is the measure of the earthquake? Second one, how is it reported in the news? Two different things. And then how is it experienced by people near where the earthquake happened, far, and other places, at the tall building, at the ground floor, or in a car? Everybody experiences the earthquake in a different way. So the experience of the earthquake, how it is reported and how it is actually measured are all very different. And how they are designed is much different from all the three of how structural engineer designed for earthquake is a very different story compared to all of them, and all of them are not directly interrelated. But somehow they are related. And that relationship is what we are looking at today. So what is the measure of the earthquake? How the earthquake is measured? Earthquake is basically, as you know, is a release of energy which has been accumulated because of the strain. And then it is measured as energy release at the source where the earthquake happened, along the fault, depends on the length of the fault, about the movement and type and all those things that many of you already know. So the measure is the energy, and how we measure the energy, we put it on a scale, and those scales tell us from the minimum zero energy to the maximum possible energy that can be generated, and that's why we have the most common scale called moment magnitude scale, which is the one that we normally report. We see the report in the news is they report this magnitude. 6.87 is on that scale from 0 to 10. The Richter scale, which some people are familiar with, was an earlier version of the same scale, but it was not so good in measuring large earthquakes, and it was quite a local effect and didn't have many other good things that the moment magnitude scale has, which actually covers the local body and surface waves together. So this is a more comprehensive measure of the earthquake, which is this moment magnitude scale, and that is the one that you normally see reported in the news. So that's the one that is the common measure now. Now, one important thing about this scale is that this scale is even beyond log. Every step in the scale is about 31 times stronger than the previous number in that scale. So if you see the energy released, it goes from this one until so many times, billions of times more as we go up. And the number of earthquakes that happen is the reverse. So a lot of earthquakes happen with lower magnitude, and very few earthquakes happen which are of a higher magnitude, and we assume that beyond 10 there is no earthquake computationally possible. So that's the scale, and then you can see a lot of earthquakes listed on this one. So this is the scale that normally people are familiar with, or that's the one that we are concerned. Now, where is our structure on this? Where is the earthquake and where is the structure that we want to design on this scale? Now, let's come to the next one. How it is reported. This is how it is reported, as I showed you. They say a 6.2 earthquake happened and many people died, bodies are being discovered, and they show the picture, buildings fallen down, completely collapsed, cars crushed, and so on and so forth. That's the image that people get of a strong earthquake that happened even at 6.2 magnitude. And then people get worried, what my house is going to do if an earthquake like that happens. And this is videos, this is news, and it flashed everywhere, and it makes everybody concerned about their community, about their house. Now, how they feel the earthquake is another issue. So when an earthquake happens, depending upon where they are, whether they're awake, they're asleep, they're moving, they're standing still, they're on a tall building, or they're on the ground floor, they experience in some way, and they feel things moving. And then, depending upon the feeling, this scale, another scale, which is the or modified Mercalli scale, is used. And this ranges from not felt 1 to extreme at this scale. And it's all related to how you feel. So now this is actually not related to the earthquake magnitude, because earthquake may be happening very far, your building may be very distant, so you may not feel it, or you may feel it some, and people near may feel differently. I personally have experienced several earthquakes of different kind in a tall building, on the ground. Last time there was an earthquake in Nepal in 2015, I was there, and when I was there were many aftershocks, and I could feel the aftershocks. We ran out of the school that we were inspecting at one point because it was so strongly felt, because we were very close to the epicenter. But the same earthquake was not felt far away. And in Bangkok, I remember the tsunami, when it happened, the tsunami happened, the earthquake happened very far in Indonesia. But our building in Bangkok actually swayed, so much so that we had to go down the building because it was swaying. And the water pipes broke in the elevator shaft, because the building was susceptible to that kind of earthquake with long period and so on. So that's another story altogether. But my point is that we all experience earthquakes in a different way, and how we experience is based on the scale, and we can say earthquake was mild or strong, not related to the magnitude, but how we experience it. So that's another scale. So this is what people think about an earthquake, but they also see what happened at another location. So this is what we have so far. First of all, we have an earthquake that happened somewhere with a certain magnitude. It was reported in the news like this, with the damage and some other things about the earthquake. And it was felt by some people at different location in different manner. So we have the earthquake, we have the reporting, we have the perception, and then the question comes, is my structure safe or not? And that's what we have been addressing in the last few discussions. And now we see that how this structure was designed is what we are now going to look at, and then we are trying to link it back to the earthquake that actually happened, not how it was reported and not how it was experienced. So how do the earthquakes affect structures? It's a complex, very, very complex phenomena. First of all, same earthquake can have different effects on different locations, as I mentioned. Different structures at the same location may experience the same earthquake differently. A tall building will respond differently. A short building, mid-rise building will respond differently. A building on the ground will respond differently to the same earthquake at the same location coming from the same source. Structures perform differently for different earthquake effects. They also perform differently whether the shock was very fast moving, was it slow moving, the frequency content of the earthquake will be important, the kind of waves that are coming are important, does it have a vertical component or not is important. So if earthquake of different type will also affect the response. Then different magnitude of earthquakes have different probability of occurrence. So that's another issue. Different earthquakes happen at a different frequency, and that is also something that we need to consider. The design earthquake loading is derived from several earthquakes and different sources for different magnitude with different probability of occurrence. So all this information is collected and analyzed, and the seismic hazard is developed by the codes or the building officials or the countries or the localities after accumulating all this data and the risk profile of the location, particular location, and then maps are made, and that's what leads to the design. And that's where the design earthquake comes from. Then we take that design earthquake and then we convert that into some kind of an input to our structure. And that input could be as simple as an equivalent static force. We just convert the earthquake, which is a complex phenomena, into just an equivalent force applied at each floor level. That's the simplest one. Second one is that we convert that into response accelerations for short period and long period effects so that we can cover buildings of different height and stiffness and mass and natural frequencies. Or it can be an acceleration response spectrum which covers a broader range of the response, or it could be a base acceleration imparted as time history, or we could actually shake the building by simulated ground motion to see the dynamic and even the nonlinear effects. So we can do any of these things depending upon the type of structure and tools and experience that we have. And mostly codes will let you do this first 2 or 3 parts, and then this one, last one, is not done that often. But none of these have direct correlation with the magnitude, as you can see. We are talking about things that, again, are far from the magnitude of the earthquake that was actually happening at a particular location of the origin of the epicenter. So then, how are we going to connect it? So basically, we start with the Newton's law of motion. Force is equal to mass into acceleration because earthquake is an acceleration. So we relate the mass of the building with the acceleration, ground acceleration, but not the ground acceleration, but the acceleration of the mass, which is actually moving because of that. And this leads to several equations, the old style in which there's a factor that adjusts the acceleration and then multiplied with the weight, and that correction includes the structures type, R factor, and many other things. And similarly, the newer version combine all of that into this factor, and this factor now becomes more complex to determine and consider more things. But basically, we're simply following the F is equal to ma with modifying it for different things. So this is an attempt to convert the acceleration response into an equivalent force using this concept. And then corresponding maps have been developed. This is a map developed with the older version of the equations, where the countries or the regions are divided into zones from 0 to 4 or 5, indicating the severity of the hazard. And people take that zone, take the acceleration associated with that zone, and then multiply it with the equation and get the force. The newer version or the newer maps incorporate more details. They talk about the return period, they talk about the various parameters coming from the response, and they also have a short period response, long period response, and then these maps are a little bit more comprehensive and they incorporate more information, and then the newer versions of the equations can use this information. Or you can use the response spectrum developed for a particular country or a region, modified by some factors for local conditions. So again, response spectrum covers a longer range of the initial periods and can be applied to tall and short buildings as well. So that's how we convert the earthquake into a way to apply that as a factor or as an acceleration that will be used then to calculate force. Or we can shake the building by a simulated time history or series of time histories, then let the structure determine the forces based on that with the damping and all of those stuff. So this is obviously more accurate as long as we have a good ground motion input that we can apply. And this is finally the equations, the set of equations or equation, the main equation that we use to compute the response of a structure for the earthquake. And basically we are talking about the nonlinear dynamic equilibrium equation, and from this we can derive the free vibration, the equivalent static force that I mentioned, the pushover analysis, the response spectrum analysis, as well as the time history, linear and nonlinear analysis. So all of that is included in this big equation, and this is what the software normally use to determine the response depending upon what input or what method we use. So structural engineers can determine the response, bending moment, displacement, and stresses and other things from earthquake based on any one of those inputs that we talked about. Once again, all of them not directly related to the magnitude. So where is the magnitude now? Magnitude got absorbed in so many factors: hazard maps, ground acceleration, response acceleration, importance factor, structure type, response modification factor R, damping assumption, damping ratio, stiffness assumption, cracked, uncracked, structural models of different kind, linear, non-linear, shell model, frame model, load factors, load combination, design philosophy. So many things happened in a structural design, and it all basically absorbed that whole hazard into these factors, and the design comes out, which now is very hard to correlate to where we started from the origin of the earthquake. So what is the possible answer to the question now, if you have done all of that following the design codes and design approaches? The possible answers are: your structure has been designed for the appropriate earthquake magnitude for the location that your structure is, with reasonable factors of safety against collapse, using the applicable design codes, using engineering practices. So we can make that statement that don't worry, your structure has been designed by considering all the earthquakes that can affect that area, and the engineering judgment and the load factors and safety factors have been designed, so you don't need to worry. But we cannot say which exactly magnitude. Or your structure has been designed for an acceleration of 0.xg, 0.2g, 0.5g, corresponding to a very strong earthquake with adequate margin of safety against collapse, which can be related to the maps again, because this acceleration is part of the map. But again, the acceleration is at the site, not relating to the magnitude once again. So these two answers are possible. One is more technical, one is more general. Whether the public will be satisfied with its answers, it depends. But it still did not answer. It's very hard to answer directly what magnitude has been used. So code-based design approach has very good intent. It basically covers 3 levels, but not explicitly, but implicitly. Service level earthquakes, moderate earthquakes happen frequently with no damage. A design earthquake is certain, which is about 2/3 of the maximum earthquake that can happen, and that is a design basis with factors, and the maximum earthquake, which is the MCE, without collapse. So that's the intent of the codes, but there is no explicit check. Performance-based design, on the other hand, can make this check more explicit and hopefully lead to a better answer of the question. Can performance-based design help to improve the answer? The answer to this question is yes, because now we may have a better way to answer the question that we started with. Through a site-specific study, we can get very, very specific information about the hazard, not a general country level or even micro-zonation map, but which is actually micro-zonation maps will help a lot, but we do a site-specific study. Through advanced and more realistic modeling of structures as designed, so we design the structure first and then we model it, so we check the performance. We don't design the reinforcement to come to one solution, but rather we check what has been design. Through more detailed and comprehensive analysis, as we mentioned in previous other discussions, and through explicit evaluation of serviceability and collapse prevention, very clear evaluation, basically going back to correlating the hazards with the performance at different levels, at different performance expectation as well as hazard level. So this is what the performance-based design can give us together with a site-specific study. So after having done that, let me come back to this light source analogy once again. This is taken from Professor Murthy's book, which I really like. I've used that in many lectures. Basically, it clearly shows that the epicenter is here at somewhere in the ground, and then we have at the surface where we normally measure it, and then there's a place of interest where the structure is made. There's a distance on both this way. There's a fault line, there's a direction, and many things. And just like a light bulb, as I mentioned, depending upon how far you are, the light may be experienced differently, and what is in between, and how what is the type of the book that you're reading, and so on. So this analogy still holds very much when we are trying to connect the earthquake magnitude to the structure. The site-specific study considers all relevant earthquake sources with their potential maximum magnitude with different return periods. That's number one. It also considered the attenuation or the transfer of that ground, the effect of that earthquake to the site, and what is in between and what is below, between the bedrock and the structure. Like for example, the basin effects in Bangkok or Mexico, all those things are considered there. And then the amplification effects and the damping effects are considered. And then correlating source magnitude and distance from the structure. So it also correlates how far the earthquake will happen and what will be the magnitude and so on. So this study basically studies every relevant seismic zone or potential earthquake point and their potential of producing an earthquake and how it reaches the site and what is the site like. And then it comes to the structure, which is the PBD. So this is very important. Site-specific study gives us that information. After having that, we can then see what is the contribution of each source or each different source of earthquake coming to the site. So we can identify, okay, this seems to be the most prominent source of the effect from this site. And then it can be in the ground acceleration, short period, long period response, and so on. So many things can be calculated with a different return period. So this will relate the effect of the earthquake, different earthquakes at different locations for the structure. This may shift if the structure is somewhere else. But here, this particular site is the one that will govern. So now we know that this is the one that we should be looking at when we look at the magnitude. It also correlates the distance and the magnitude with the fractional contribution. That means what is the relative contribution to our total risk from different sites located differently at different locations with different magnitude. So again, it tells us, oh, this is the one that we should be looking at because this has the highest contribution. So we should be looking at the magnitude of this earthquake at this distance. So we can say from here that, okay, 10 kilometer far earthquake with 6.7 or 6.8 magnitude, this is the one that is going to be of more critical impact to our structure. So we have more or less identified now the magnitude of earthquake for which the structure is primarily designed for, including all the effects of the other earthquakes that might happen. And then after doing the PBD, we can actually determine the strains and stresses and response, and we can check everything, whether the wall is yielding or cracking, or whether the coupling beams will be okay or not. So we do all those checks, and we know that these ground motions derived from those locations have all been considered with different frequency, content, and so on. So it's a very comprehensive analysis that gives us some level of confidence that, okay, this structure is going to be fine, or this part is going to be damaged, but this part not going to be damaged. And with all that information now, we have an alternate answer, which is close to what we want to get. So now the answer can be, your structure is capable of resisting a magnitude N earthquake happening at a location A with a probability of occurring every 2,500 years. So we can say, okay, For example, for Bangkok, for a long time people believed that earthquake is not a hazard, and people didn't design the structures for that for a long time. And because there was no near fault, there was no earthquake sources nearby. But as the knowledge developed, then we know that, okay, even though we don't have an earthquake near Bangkok, but earthquakes happening in, let's say, in Myanmar, in Mandalay region, or in a northern region, can actually affect the buildings in Bangkok, including the soft soil that we have here, buildings especially in the range of 20 to 25 or 30 story. So that has been now determined through all these site-specific studies and the performance-based analysis, and now we can say, oh, an earthquake 6.7 magnitude in Myanmar will be very critical for a building having 25 stories in Bangkok. So that's how refined our answer can be. Or a 5.5 earthquake in Chiang Mai, for example, will have similar effects and so on. So now we can be very clear about the magnitude for which the buildings are designed, not only in a region but a particular location. So a 5-story building will be affected by a different kind of earthquake, and a 20-story building different, and a 50-story building different. We can also say that this structure can resist an earthquake of magnitude M happening at location B with a return period of 50 years without any damage. So serviceability can be confirmed or can be reported related to the magnitude and location and the occurrence interval, and the safety can be also connected to magnitude and location and occurrence. So this is what we can get from PBD, which we could not clearly get from Codebased unless we know a lot of background on the development of the seismic risk maps of the location. So now we can conclude, or we can summarize. Designing structure to safely and serviceably resist the effects of earthquake is a complex process. We know that. It involves too many things, as I mentioned. Too many unknowns, too many assumptions, and too many complexities. The intent of the design codes is to provide us with the framework so the structures can be designed safely for the applicable hazards at that location, which is a combination of all the hazards coming from the different areas with a certain factors of safety and so on. If structures are designed using code-based approach, it is hard to link the safety with the specific magnitude and location, because the maps do not clearly tell us that, and we haven't actually done an evaluation for the design anyway. We have simply followed the code with all the factors included there. If performance-based design is used, then we can actually identify the controlling earthquake from a location with the probability of occurrence to say this is the structure that really governed, because we have looked at the time history response from every earthquake, and we can see which was the maximum one which controlled the design or controlled the output for different locations. Remember, different parts of the structure may be governed by different earthquake and ground motions or time histories. It's not because it depends on, that's why we do 11 or 33 or more ground motion analysis, because we want to capture the response from every possible variation. So that's what we have when we try to respond to the question, what magnitude earthquake our structure has been designed for. I hope this discussion will lead to some more insight and as well as some more questions. So thank you.